Let us next see exercise 5. Here n is a positive integer and we have a list of 2n real numbers. Because it's a list, the numbers are not necessarily distinct. The ai's that you see here from a1 all the way up to an, there may be repetitions in them, and the equal number of bi's, there may be repetitions. In fact, some ai may be equal to bi also, some bj. But anyway, for these real numbers, we have to verify this identity, this one. So what does the identity say? So in this identity, you first take the products of the corresponding ai's and ai and bi. So you get ai, bi, and you take the sum of those products. So that way you get this sum where there are n terms, and you take the square of that sum. With that, you add this double summation, or you can call it a sum of sums. In this outer sum, the index I varies from 1 to n. For each such I, you are getting one sum, that is the inner sum. In the inner sum also, j varies from 1 to n independent of I, and there is a 1 over 2 here in front, and the terms are these: ai bj minus aj bi whole square. So this entire thing should be equal to the product of these two sums. Each sum is the sum of squares of these numbers. One of them has the ai squares and the other one has the bj squares. And of course, again, I and j both vary from 1 to n independent of each other. Actually, this is not the entire exercise. There are other things also after this. But let us first verify this identity itself, and then we will see the other parts. We are going to prove this identity by induction on n. So accordingly, we start like that. We apply induction on n. The case n equal to 1 is trivially true, which will be the basis for our induction. How is it trivially true? What happens when n is 1? If n is 1, then there is only one a and one b, and they are respectively a1 and b1. So in that case, what happens to the left hand side of this identity? Let's see. Because n is 1, this sum has only one term, and that is a1 b1. So this square is a1 square b1 square. What about this? Here also n is 1, so the only value that both I and j can take, they are equal to, that is equal to 1. So that means here we will have a1 b1 minus a1 b1. So it is 0. So that means in this special case, this second term in this sum is 0. So the left hand side is a1 square b1 square. What is the right hand side? Here also n is 1. So this sum is equal to a1 square and this one is b1 square. So yes, on this side also we are getting a1 square b1 square. So that is why it's trivially true. And then the induction hypothesis. Assume that the identity is true for some positive integer n. And now we will go for the induction step, where in place of n we are going to now choose n plus 1. So let's see how that goes. So for our induction step, next we choose these real numbers. C1, C2, if you want you can call these also A1, A2, etc. For some reason I decided to write C and D. So C1, C2 up to Cn and then Cn plus 1, because we are now going for the n plus 1 case. Similarly D1, D2 up to Dn and Dn plus 1. So these are my real numbers now. And for these real numbers, I considered the left hand side of our identity. So this time, this first sum will have, here the index I will go from 1 to n plus 1. And accordingly, the second term also looks like this. Now let me first tell you the plan. Okay, what should we do after this? See, the plan is to create a situation where we can apply the induction hypothesis which according to our assumption is available to us, where we have the identity for n. That means somehow from the first sum we have to take one term out and keep the remaining n number of terms, so that we get a part of that identity, the left hand side of the identity. So what we have decided is to take out the last term of this sum, Cn plus 1 Dn plus 1, which you obtain by putting I equal to n plus 1. You cannot, of course, however, simply just take it out because there is a square. So we are going to write this first sum as the sum of the first n terms plus the last term, and then we will apply a plus b whole squared formula. That is one thing we are going to do. And similarly, we are also going to break these sums down. So let's see how it all goes. So this is the first split. We have written this sum as the sum of the first n terms plus the last term, Cn plus 1 Dn plus 1 whole square. And for this second term, this second thing, what we have decided is we would write the outer sum in two parts. Here also we are going to consider the sum of the first n terms. So you can see that originally I varies from 1 to n plus 1, but now I have made I vary from 1 to n. That means I am not writing the last term in the outer sum, which corresponds to the I value n plus 1. So which I have to write separately. So for this you can see that the inner sum hasn't changed here. Summation j from 1 to n plus 1, and of course the term is whatever it is. But then I have to write this entire thing for the specific value I equal to n plus 1. Now because I am writing for only one I value, this outer sum, this thing vanishes here because only one I value. And that value I have written here. So you can see that in place of I, here we have n plus 1, d n plus 1. But again, the inner sum, apart from writing I equal to n plus 1, remains the same. Here j still varies from 1 to n plus 1, and 1 over 2 is of course there. Now in the next step, we are of course going to expand this square. And what shall we do with these things? Let's see. So we expand the square first. This square plus this square plus 2 times this, which we write slightly differently. We write Cn plus 1 Dn plus 1 first, and then we write this sum. So that way we don't have to use another set of brackets. Plus, now what we are going to do with this one is there will be two things. The first thing is that from here also we are going to take the value j equal to n plus 1 apart, or rather I should say we should take the term that corresponds to that j value outside. Okay, outside means we take it separately. That is one thing. And you carefully note this sum. What will happen if you put j equal to n plus 1 here? That means what happens to the last term of this sum if we write the sum out as a sum by first putting j equal to 1 and then j equal to 2, going like that. If you put j equal to n plus 1 here, what do you get? Cn plus 1 Dn plus 1 minus Cn plus 1 Dn plus 1. So that term actually vanishes. So you can just write j equal to 1 to n here, because there is no need for writing the last term. So that's the thing that we are next going to write, because this step is not complete. So let's see. So continuing from here, we do just that. Just that means this time the outer sum remains as it is, but the inner sum is split into two parts. In the first part, j varies from 1 to n. So that's what you see here. Okay, so that's how we get one thing, one term, plus the other part consists of the term which corresponds to j equal to n plus 1. But note that although that is one term, but the outer sum, this one is still there, where I varies from 1 to n. And what shall we get if we put j equal to n plus 1 here? Cid n plus 1. Cid n plus 1 minus Cn plus 1 di whole square. Okay. And what did I just say about this sum? That you can write j as varying from 1 to n because the last term vanishes. So that's what we also did here. Now in the next step, we quickly gather those terms together for which we are doing all these things. That is, which will give us a situation where we can apply our induction hypothesis. That means we are taking this term, we have written that here, that square of the sum, where only n terms are involved, not n plus 1, plus this term. Because here also in this double sum also, both I and j vary from 1 to n. In the original one, both of them varied from 1 to n plus 1. But that leaves us with what? What else is there? So we have taken this one, we have taken this one. That means we have 4 extra things. This Cn plus 1 square, Dn plus 1 square, then this thing, then this thing and this thing. Let us think of these things afterwards. What do you see in these two sums? At once they look different because you see Cin plus 1 minus Cn plus 1 di. Here however Cn plus 1 dj minus Cj dn plus 1. Now let me make the changes here itself. Is it okay if I write I in place of j? Yes, that's not a big problem because the index in a summation is after all a dummy variable. Doesn't matter whether you call it I, j or by some other name. So let me first do that. Okay, so I change j to I. Here also in place of j I have I. Now what do you see? They look almost like the same thing, but not quite. Still we have Cidn plus 1, here we have minus Cidn plus 1, minus Cn plus 1 di plus Cn plus 1 di. But actually these two are equal because these are squares, not simply these differences. So here you get the nice fact that these two sums are actually equal. And we have a 1 over 2 in front of both of them. So if you take their sum, that 1 over 2 will turn into 1 and you can write just one sum. That's what we are going to do, besides also writing these things. So let's see how all this goes. And we write the other terms like this. First we write this term, then plus that term where you have 2 times Cn plus 1 Dn plus 1 times summation of Ci di. So we have decided to take the 2 Cn plus 1 Dn plus 1 inside and do a little arrangement like this. We write like this: 2 times Cn plus 1 di times Ci Dn plus 1. You will see why. Plus combining these two sums, because we have just now seen that they are actually the same sum, we can write plus this sum, where now there is no 1 divided by 2. And we have decided to write this one, Cn plus 1 di minus Ci Dn plus 1 whole square. Now what will happen in the next step? In place of this entire thing, we are of course going to write one summation times another summation by the induction hypothesis. So that will be done here. Now you momentarily forget about this. You concentrate on this and this, and here also you forget about the summation symbols for a moment and think of this single square and this single product. What do you see? Cn plus 1 di minus ci dn plus 1 whole square. If you expand this square, what shall you get? This square plus this square minus 2 times Cn plus 1 di times Ci dn plus 1. Here you have plus 2 times Cn plus 1 di times Ci dn plus 1. So they will cancel out. So that means if we expand all the squares which are the terms of this sum, then the 2 times part, all those parts in this square, they cancel out with all these things which are available there. They are negative versions. So then what shall we get in the next step? So in this next step, this part of course, as I said just now, comes from the induction hypothesis. Summation Ci square times summation dj square, where I and j both vary from 1 to n, plus. So we expand these squares, those cancellations they happen, and we write the square terms like this as two sums, okay, which we can of course do because addition of real numbers is commutative as well as associative. Because of these two properties, you can rearrange the terms of a finite sum in any way you want. So that's how we are getting these two sums as well. The first one consists of these terms Cn plus 1 square di square, and the second one consists of Ci square dn plus 1 square. Now I am going to straight away write the last step, and then from the last step we will come back and see how this entire thing is equal to the last step. Let's do that. And the last step is this, what we are supposed to ultimately get, where again we have one such product, but this time I and j both vary from 1 to n plus 1. Is it really equal to the previous step? Let us see. What will happen if you multiply these two sums? In what way I am telling you? You write the first sum, first sum means this one, not this one. You write the first sum in two parts, again as before. In the first part you only consider the I values from 1 to n, and in the second part only I equal to n plus 1. That means you are writing summation Ci square where I goes from 1 to n plus Cn plus 1 square. Similarly you do this one also, summation dj square where j goes from 1 to n plus dn plus 1 square, and then you do multiplication. You will see that you are actually getting these two things. Just think about it for a moment. The two sums that you have here in these two factors are these two sums. So they will get multiplied. Besides that, you will also multiply Cn plus 1 square and this one. What will that give you? Cn plus 1 square times summation dj square where j goes from 1 to n. You don't see j here, but you can write j in place of I. The name does not matter. And also you will multiply dn plus 1 square from this side and this sum where I goes from 1 to n. So that way you will get this summation dn plus 1 square times, no, not that actually, sorry, dn plus 1 square times summation ci square where I goes from 1 to n, and that is what you see here. And there is one more thing, the multiplication is not complete. You are also going to multiply Cn plus 1 square and dn plus 1 square, that is here. Okay, so this really is the previous thing. So that's how you have got what you wanted to get, that is your right hand side of the identity where you have n plus 1 now in place of n. So this completes the induction. So let's write these things. Okay, so all of this completes the induction and proves our identity. Now let's go to the other parts of this exercise. With the help of this identity proved just now, we have to conclude the Cauchy-Schwarz inequality. This is a very important inequality. What is this inequality? Again, we have those AIs and BIs. Okay, A1, A2 up to AN and B1, B2 up to BN. This time we are considering the absolute value of the sum of AI, BI, where I varies from 1 to n, no squares or anything. The claim is that this is less than or equal to this product, where we see square roots, square root of the sum of the squares of the AIs times the square root of the sum of the squares of the BJs. Before we go for proving this, actually once we have this identity, now proving Cauchy-Schwarz inequality is very easy. We no longer have to apply induction or anything. We can directly do it. But before we go for that, let us just note one thing. Does it make sense to consider square roots of these sums? Do not forget that we are working with real numbers. So when there is a square root, you should be careful. That is, you should not have a negative number whose square root you are taking. There won't actually be any problem. You will get non-real complex numbers. But that's not what this identity is about. Actually, you see, if you get a non-real complex number here, then this inequality will become meaningless, because there is no such inequality between complex numbers, which behave very well with the algebra of complex numbers. But anyway, the thing is that we should make sure that general complex numbers should not appear here. That's not a problem here anyway, because the sum involves only square terms. So the least they can be is 0, no negative. So there is no problem with these square roots and they exist. Now let's prove it. So we start the solution like this. Although in the original inequality there is no square, but we do start with the square of the left hand side. Okay, square of the absolute value of summation AI BI. Now you know that when you take the square of the absolute value of a real number, that is equal to the square of the real number itself. Because mod x, where x is a real number, is either plus x or minus x, and the square of either one of them is equal to x square. That's why. So now you can see that if you go back to the previous inequality that we proved by induction, this is one term in the left hand side of that, identity. This is one term of the left hand side of that identity. The other term is not present here. What will happen if we write the other term? We are likely writing more, because whatever this entire double sum is, it only involves sum of squares which are by their very nature non-negative real numbers. It may happen that ultimately all these squares are 0, but if any one of them is positive, we are writing more. Otherwise, we are not changing the size of this, but we are not writing less. That is why this thing is less than or equal to this plus this. Non-negativity of this gives us this inequality. But by the previous identity, this plus this is equal to this. That means this square is less than or equal to this product. Now take square root on both sides, and while doing so, make sure that the individual things whose square roots you are taking are themselves non-negative real numbers. There is a modulus, so this is non-negative, and these are non-negative, we have already seen. So this side becomes ordinary absolute value. On this side, actually the square root is over the entire product. but by one of the rules of exponents that we see way back when we were studying those things. Just like you can distribute a square over a product, you can also distribute a square root over a product. And finally, the last part of this exercise, where we have to use the Cauchy-Schwarz inequality proved just now to prove the triangle inequality. Here, all the terms have square roots. Square root of summation of ai plus bi whole square, not ai bi. Okay, and this time here also we have square, unlike this one, and that is less than or equal to the square root of this plus the square root of this. Square root of this means these two things are added here. Here they are multiplied. So let us now prove this triangle inequality. Okay, so we start the solution like this. The original inequality has the square root of this sum, but here we are considering only the sum. So we will take square root when it is convenient. So what we do, we expand each square term. So that way we get ai square plus bi square plus 2ai bi. And then we make sums out of those things. Okay. So summation ai square plus summation bi square plus summation 2ai bi. In the next step, we will replace this real number by its absolute value. Now every real number is less than or equal to its absolute value. If the real number is non-negative, it is equal to its absolute value. But if it is negative, then it's strictly less than its absolute value. In general, this is less than or equal to this. Where of course we have taken 2 outside. First of all, outside the sum, and then it went outside the absolute value as well because it is positive. So that way we are already getting an inequality. And now this is where we are going to apply our Cauchy-Schwarz inequality. So in the next step, but before we write that thing, we also do something here to these two sums. We take the square of their square roots. That will give the original sums, but be careful. In order to do this, the thing on which you are doing this has to be a non-negative real number. Yes, they are non-negative real numbers. So that's how in place of this we have this, and in place of this we have this. Oh, and one more thing. Here, in anticipation of what's going to come next, we are using the index name j in place of I, which we can do, plus this. And this is coming from this term via Cauchy-Schwarz inequality. So what do we have now? Something square. So let us call this square root a. Okay, say capital A, plus something else square. Let's call this b. A square plus b square plus 2 times a times b is a plus b whole square. So you have square on this side, and the term that you started with, that however did not have any square. It's also non-negative. So you can now consider this inequality. In fact, that term was summation ai plus bi whole square, as I varies from 1 to n. That is less than or equal to this. So now you can take square root on both sides, and that will give you your triangle inequality. So you can write the last line yourself. And let me end the video here itself. So tomorrow also we have our upload. So let's see what we have tomorrow. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.